Is everyone good? Okay. So, welcome to the technical review of Bitcoin. So, if you recall back to Nadir's first lecture, he talked about how Bitcoin worked at a high level. So today we'll get into like the nitty gritty. We'll talk about how the Bitcoin protocol is implemented and how it actually works at a technical level. To give a general outline, first we'll cover cryptographic hash functions, and we'll talk about what makes Bitcoin a tamper-evident database. And then Gillian will take over and start talking about signatures, Bitcoin scripts, and how money is actually redeemed in Bitcoin. So first, let's talk about cryptographic hash functions. And before we get to why we use cryptographic hash functions, let's talk about a bit of the motivations why we even use this type of algorithm. So we discussed that Bitcoin was a trustless environment in which the protocol allows us to come to consensus on information without a central third party. How do we verify that the information is correct and not manipulated? So in this trusted, in this trustless environment, we might have information like unreliable information storage or delivery. So let's say I was sending a message to Sarah, but through Gillian. What's to prevent Gillian from tampering or messing with the data before she passes it on, right? So for this reason, we want a way to create tamper detection when we're dealing with this information flow. So how do we actually solve this problem? We fingerprint everything, right? So fingerprints introduce this idea of standardized randomness. So I'll talk a little bit about that. So the randomness aspect of a fingerprint comes from the fact that we can't really choose what fingerprint we end up with, and we can't reliably predict what someone's fingerprint looks like. We use fingerprints to identify people since it's unique to every person. However, we still want it to have a standardized structure, meaning that everywhere you go, the bank, the DMV, your phone, reads it all the same. So if someone can ever fake our fingerprint, or if someone has the same fingerprint as us, they can pretend to be us, and we don't want that to happen. So how do we actually implement the idea of fingerprinting or standardized randomness in Bitcoin? We use cryptographic hash functions. So anyone know in math like what a function is, right? So if we have a function f, we give it some input x, and we spit out an output f of x. We call it the x, the input, and we call the output f of x, right? So when we're dealing with hash functions, we just change a few letters around. So if we have a hash function h, we provided an input x and output h of x. We call the x the pre-image, and we call the h of x the image, right? So in Bitcoin, when we're using cryptographic hash functions, there's specifically three properties that we really care about. One, pre-image resistance, second, pre-image resistance, and three, collision resistance, right? These are the equivalent of mathematical fingerprints and identifiers. So if we look over to the side over here, if we look at this picture, we can see that each of these inputs produce very different outputs. Keep in mind that two main ideas. First, that hash functions need to be practical, meaning that you can't take ages to compute what a hash function is, right? Or else it won't be very feasible, right? So we also want hash functions to be deterministic, meaning that the same input will always yield the same output, no matter where or when you compute this hash function. And that's important because we don't want different outputs to map to the same input and vice versa. So we don't want a small change in the output to ever reflect anything different, right? So we want each of these inputs to be very similar. Or no. My bad. We want to use these as a reliable identifier. So each of these inputs, despite being very similar, might produce different outputs. So we want a reliable and unique identifier for these types of situations, right? So first, let's talk about pre-image resistance, right? So given h of x, it is computationally difficult to determine what x is. So we don't want anyone, if we want to disguise our information and we don't want to give out our output that doesn't reveal the input itself, we don't want anyone to reverse engineer our data or our output and find out what our input is or our information that we want to hide. The output should be a separate identifier that we can't really extract from any information from. We can't extract any information from our given input, right? If we use our fingerprint analogy, let's say we find a fingerprint. We want to, the question that we ask is, whose fingerprint is this? It should be difficult to find a given person seeing a fingerprint out in the wild, right? So second, we have this idea of second pre-image resistance. So given x, it is computationally difficult to find some value x prime such that they have the same hash, right? So you don't want someone to generate some input that will masquerade as your input. So this is extremely important when, let's say, when we're dealing with transactions, right? Let's say I have a hash of a transaction and someone comes along and finds another transaction that generates the same hash, right? We don't want this person to, I guess, claim that a previous transaction that I conducted in the past was actually theirs when it was actually mine, right? So this becomes extremely important when we're dealing with transactions. And the analogy that we use for fingerprints is, can you find someone with the same fingerprint as you, right? When we're talking about collision resistance, the formal definition is, it is computationally difficult to find an x and a y such that the hash of x is the same as the hash of y. So this is, it might seem similar to the previous slide, it might seem similar to a second pre-image resistance, but it's a more general case. Collision resistance is saying that in the general sense of things, we don't want any sort of pair of hash or inputs to ever collide with each other, right? In reality, you'll always have collisions, but we want it to be difficult to find these collisions. So the fingerprint analogy that we use for this is that, can you find two random people with the same fingerprint, right? And moving on, we also refer back to the idea of an avalanche effect. So some small change in the input produces a pseudo-random change in the output. So what that means is, it alludes back to the first slide. If we were looking at this picture right here, we want similar data, no matter how similar they are, to produce different outputs, right? In other words, if someone is trying to guess the input, we don't want them to play this game of hot or cold and try to figure out what some input is by just playing around with the output that they see. So there should be no correlation between a change in the input and also a change in the output. Does that make any sense? Does anybody have any questions right now? I went over this a little bit quick, but yeah. Yeah.
So typically, is the function, the hash function, one-to-one?
It has to be at least one-to-one because you want to be able to find, you still want, to, that's interesting. Actually, I think it should still be one-to-one, but it should be difficult to find the inverse, right? So you can probably still find the inverse, but you don't want it to be easy to find the inverse. Yeah.
Clarify, it's a one-way function, so your output
Yeah.
space is actually smaller than your input space, so it can't be one-to-one.
Oh,
But
yeah,
it's one-way.
that's actually correct. Yeah, my bad. So the specific cryptographic hash function that Bitcoin uses is SHA-256. It's a function designed by the NSA. It takes input of arbitrary length and it outputs or spits out an output of 256 bits. Specifically in Bitcoin, they use what's called SHA-256 squared, which is basically they take the output of your SHA-256 function and they SHA-256 it again. That's a design choice by the Bitcoin developers, but that's what Bitcoin uses to that's what Bitcoin uses as its cryptographic hash function. Yeah.
I know it says C readings for clarification, but what is the benefit of SHA-256 in the SHA-256 hash?
Doing it twice, I think it's just a design choice by the developers. I don't think it adds any extra security on top of it. I guess it obfuscates the input a little bit more. Yeah. So, does anybody have any more questions on this cryptographic hash functions section?
Sorry, can you go over the avalanche effect?
The avalanche effect. Okay, yeah. So the avalanche effects, it's basically saying that any change in the output. Let's say if I have the letter A and I hash it and I get an output of the hash of A, right? Let's say I just change it to the letter B, or I add, let's say, AB to it, okay, or something like that, right? Even though the inputs seem very similar to one another, their outputs should be, or not completely different, but it should add a pseudo-random change. They could be by chance that the outputs are similar, but in the general case or in the average case, they should be very, very different. So if you look at the picture here, so even though all of these inputs, I am Satoshi Nakamoto with a number concatenated at the end of it, they produce drastically different outputs, even though their inputs seem very, very similar. Yeah. It's basically to prevent people from guessing or playing guess and check with the system and trying to game the system. So next, we'll talk about what makes Bitcoin a tamper-evident database. So this is, in essence, what a block looks like. In the blockchain. So it has these main components: a block header, previous block hash, and a nonce and a Merkle root. All of these are there's more to what's in a block, but these are the core components and what makes up what's the most important in a block. These parts, if you refer back to Nadir's very first lecture, all of these three refer back to each of a section in the high-level overview. The Merkle root is a summary of the transactions that go on. The previous block hash allows you to create this ordering of transactions, and the nonce is the proof of work aspect or the consensus mechanism that we used in the Bitcoin blockchain, right? So let's begin by talking about the block header. So this block header is, a summary of the previous block hash, the Merkle root, and the nonce. They're all concatenated together, and we have a unique block ID from the hash of all our information that we have here. So if we talk a little bit more about these individual components, let's say the Merkle root. The Merkle root is, if anyone has seen does anybody know what a tree is in computer science? How many people know that? Yeah. So a Merkle tree is basically a binary tree of a bunch of hashes. So on each level, we have hashes of the previous level. So at the very, very base, we have all our transactions that we want to include in a block and that we want to verify, right? So in the next layer up, we take the hash of our transactions on the previous level, and then we create we create a separate level, right? And then in the next level up, we take a pair of hashes, and then we hash them together. So it all bubbles up into what we call a Merkle root. So this Merkle root is a hash of its child transaction or hashes, and then we can see that most of it all stems from the transactions that we're including. So if we were to, let's say, change a transaction in our Merkle tree, let's say we change to transaction 3, it modifies the hash of transaction 3, and it modifies the parent of that, and it also bubbles or propagates to this Merkle root. So if we see that this Merkle root is different from some other Merkle root, we can see that somewhere in our information sharing flow, someone played around with a transaction. We don't particularly know where it came from if we were just looking at the 2 Merkle roots, but we know that something was changed or something was tampered with, right? Another question I want to bring up is, do we have to have all our transactions to verify that a Merkle root is valid? Let's say we only want to include one transaction in our Merkle tree. Is it possible that we can still form a valid Merkle root just using one transaction? So I guess the idea is that as long as you have hashes of the transactions that you don't want to include already, you can form a valid Merkle root. So let's say we only want to include transaction 1. If we have B and F, we have a valid Merkle root. Does that make any sense? So we don't have to include, I guess, layers beneath it, but we need to have a way to, we need to have, let's say, the hashes of the transactions that were not included, basically. Okay. Any questions?
Go back
Yeah.
to the previous slide.
Yeah.
So how do you find that hash, like the B is really the true hash of the B of transaction?
So the idea is that, I mean, we still need the transactions, but to generate the hash, we don't need the transaction after we find a hash afterwards. So we don't have to include all the transactions in our Merkle tree, as long as we have, as long as we even have E and F, we're good, technically. Yeah.
Are all of these independent transactions?
Yeah, so each transaction is, what's it called? They're all, I guess, different transactions. They don't necessarily have to be, or they're not the same transactions. So every one is like unique. Let's say I have a transaction between me and you, and you have, let's say, another transaction between you and someone else, right? So those are 2 separate transactions that might be included in, let's say, this block. Yeah.
Could they be like totally parallel, like the people don't overlap at all? Just like any.
Yeah. So you can have like 2 completely different parties having transactions. The whole idea is that we have all these different transactions that we want to like verify. We put them all together on the space level of the Merkle tree, and then we generate a Merkle root out of that. Yeah.
And I'm just trying to relate this back to the fingerprint analogy.
Yeah.
So if someone wanted to tamper with the ordering, they would then need to sign a transaction with their fingerprint. But because that's going to be different, it then changes the hash of the Merkle root.
Yeah, so if you were to, I guess, let's say we already have a valid Merkle tree that looks like this. If I were to go back in time and, let's say, modify one of the transactions and change it to something that shouldn't be there, let's say I was trying to, I guess, create, like do a double spend attack, basically. Let's say transaction 3 is you're trying to send me money, but then you change it so that you're sending money back to yourself. If we see that we already have this established Merkle tree or Merkle root, when you go to change transaction 3 by modifying it to you sending money to yourself, it reflects back in the Merkle tree, and you get a different Merkle root. So because the input is a little bit different, it completely changes the whole thing. Yeah.
I understand that the example is for transaction, but is this also implemented on block level? So each block is verified by all the hashes of previous blocks?
So I'll get into that. That's like the next thing. So this is first the Merkle root aspect of our blockchain. If we go to the next section, we'll talk about in a block we have the idea of a previous block hash. So what that is it refers to this ordering of blocks, right? So yeah, so it refers to all the previous blocks, but the previous block that was added to the chain, and it creates this ordering of blocks or transactions that you can, I guess, deem to be the valid blockchain, right? If we were to, let's say, modify one Merkle root in, let's say, one block, it invalidates all the subsequent blocks in the future because you tampered with something in, let's say, this point in time. Everything after that is also invalid because this is an invalid block. So the idea of having the previous block hash, one, it creates this idea of an ordering, but it also adds on to the fact that you're able to, I guess, you're able to identify whether or not some block in the chain is valid or not. Does that make any sense? So the previous block hash is the aspect that allows you to create this blockchain kind of, I guess, data structure or linking between blocks. And once you have, I guess once you have valid blocks, it all comes together, yeah. Any other questions? That section was a little bit short, but. So the next thing that we include in our block is idea of a nonce. So the nonce is more so the proof of work aspect of our blockchain. So we're gonna go into a little bit about mining. So in Bitcoin we have what's called a partial pre-image hash puzzle. So we want to find a nonce that when we hash everything together in our block header, it's somehow less than some target that we're looking for. So the idea is that this nonce is, we don't know what this nonce is, but we repeatedly guess and we try to find a nonce that works, that falls under this inequality. So it's used to implement the proof of work aspect in Bitcoin and other proof of work currencies. And these hash puzzles have three, I guess, necessary components. They need to be computationally difficult. So one way I like to think of this is if proof of work requires little work, then what's the real point, right? Second of all, it needs to be parameterizable, meaning that we want to be able to change the difficulty so that it's not at a very constant difficulty, right? It can get harder and harder or easier as the network difficulty goes up and down. And it needs to be easily verifiable. So it should be, you don't need some, I guess, central authority or central third party to verify that some block ID is valid or not, or if it solves this hash puzzle. All the other miners in this network have the capability of doing this verification process. So when we're talking about mining, we can think of it as throwing darts at a target while blindfolded. So you have an equal likelihood of hitting any part of the target, but the faster you throw, the more hits you get in per second, right? So how that correlates to mining in Bitcoin is if you have more computational power, you're able to generate more guesses in the same amount of time. So what these miners try to do is they're trying to find a hash of our block ID so that it satisfies some target, right?
Can you elaborate what is the target?
So the target is we want to find some hash that has some arbitrary number of leading zeros. That's the technical aspect of it. We're trying to find some hash that has I guess, leading zeros in it, but we don't know what hash will generate those specific hashes. Or we don't know what inputs or what nonces, when if everything gets hashed together, will generate those outputs with a certain number of zeros, right? So the idea is that we just keep guessing what this nonce is. We increment things so that we can find a hash that satisfies this requirement.
So the target is like a number of attempts?
Or not attempts. It's our resulting hash needs to have a certain number of zeros in its hash. Does that make any sense? So let's say we already have a previous block hash. We have a macro. So those are already decided. We're trying to play around with this last parameter, the nonce, so that when we generate an output, the hash has a certain number of zeros in it. And the idea is that because these cryptographic hash functions are, they have this idea of like an avalanche effect. We can't really guess which inputs will get you a output with that number of zeros, basically. So the idea is that once you solve this, once you find a target with the given number of zeros that you want, once you find a target with a given number of zeros, it shows to like, I guess, the network that you've put in the work necessary to guess all these inputs to find a valid like block ID. Okay? So the difficulty aspect is it's the representation of an expected number of computations to find a certain block. So I just talked about how you need to find some hash with a certain number of leading zeros. And this difficulty we can change. It's dependent on it's dependent on like the previous 2 weeks, I guess, computational power. So how many blocks were mined in the last 2 weeks, and then we scale the difficulty up or down as the network difficulty changes every 2 weeks, right? So if we were, let's say, if we have the difficulty at 10, so what's the new difficulty when if our 2 week period, in our 2 week period, we have the same number of, we mine the same number of blocks as the previous 2 weeks, basically. So, yeah. Does anybody have a quick question? I mean, or an answer?
Oh, not an answer.
Okay, so because we mine the same number of blocks as in the previous 2 weeks, we have the same ratio, so our difficulty stays the same, right? The idea is that if our time to mine changes, let's say to 1 week rather than 2 weeks, or like if our network gets more and more difficult, or if it gets more easy, we change the difficulty to be higher. And then if we take longer, or the network difficulty becomes more and more hard, we scale the difficulty down. So the difficulty aspect of our hash puzzles can be changed. It can be modified depending on how many people or how much computational power we have in the given network at a certain time. So difficulty is inversely proportional to time to mine. And this is a general like pseudocode for mining. We have some target that we're trying to like satisfy, and we just repeatedly try to find a hash or a block header that will satisfy our target. So let's say if SHA-256 of our block header satisfies this target, it means that we found the block. Yeah.
Two questions. One is this the standard algorithm, or is
this is
the algorithm exactly like this, or
this is just like some pseudocode that essentially this is what the miners are trying to do.
is there any advantage to basically not start from zero like everybody else?
You okay?
Because I feel like, okay, the reasoning behind that is I feel like if everybody begins with 0, then it's guaranteed that the person with the greatest computational power is 100% always going to answer first. Right?
I mean,
but
this
if you all
is.
begin with 0, you might like get lucky and you just start picking any number.
I'm pretty sure like mining in the real world is a little bit different. It's not necessarily you keep on playing. You don't necessarily start from 0. And there's also other parameters in a block ID that you can play around with, like timestamp and whatnot. But those are other aspects that you can play around with. But the idea is that you incrementally check things so that you have like a standardized way of like verifying, oh, I'm past a certain point. I probably already checked everything before it. I mean, you don't have to start at 0. You can probably randomly guess around. But this is just like pseudocode that is just like a standard way of what essentially what miners are trying to do in the network. They're trying to find some random nonce that will give them a valid output. Yeah.
The second part of the question is, so you mentioned that the difficulty would adjust automatically every 2 weeks. Does this mean that we don't necessarily need this much? Like, let's say the computational power used to mine Bitcoin is double.
Yeah.
That means like this will not lower the transactional cost
Or
the time to solve the puzzle.
So if your network difficulty goes up, right? Or your computational power goes up, let's say it doubles, it means that the time or the number of blocks that you mine in a 2-week period increases significantly. And the network sees that, or the protocol sees that, and then adjusts the difficulty for the puzzles based on that. So if, let's say it like your computational power doubles, you'll have the difficulty will become increasingly harder because you'll mine more blocks in that 2-week period than any other in, let's say, when you weren't doubled in computational power, basically.
So doesn't this mean that if, like, let's say half the miners in China, for example, they're banned, no longer mine, so the computational power is like cut in half, right?
If it's cut in half, then the network difficulty scales downward
So it
because
scales, but that wouldn't affect the transactional time cost, right? Because the adjusts the problem, the difficulty level.
it adjusts the difficulty so that you have an average block time of 10 minutes. It doesn't, you don't change the cost. The cost has nothing to do with, yeah. So does that answer your question? Yeah.
So this whole thing seems kind of weird because essentially we established some properties of SHA-256, which is that it's collision resistance and pre-image resistance and all this stuff. But now what we're doing essentially is partially inverting SHA-256, right? That's what the whole point of this is. And it seems like we can, do a partial inversion of the SHA-256 every 10 minutes. So what I don't understand is, and I understand this is a partial inversion because there are only some properties that we're trying to satisfy, like some leading zeros or something like that. But isn't this kind of dangerous? Because I imagine that if we take the entire Bitcoin network and we take all of the computation in the entire Bitcoin network, we can actually target a user and essentially invert SHA-256 to find their private key from their public key in the same manner, right? Is that like if the entire Bitcoin network decided to target a user, and in 10 minutes if we can do this, then how long would it take to actually invert it entirely and find someone's private key?
That's a very good question, and I'm not completely sure how to answer that. I want to say that your public key, your private key, and like those aspects, your Bitcoin address has, I guess, it's generated not just by SHA-256. The mining puzzle might be only using SHA-256 to, let's say, create, find a certain property. When you're dealing with the identity aspect, so the mining aspect and the identity aspect are slightly separate, but they still use the same, I guess, hashing algorithms. When you're dealing with like generating like identity, like private key and public keys, using SHA-256, they have some other factors added on top of it, so that it's not just SHA-256. Like the actual generation of like Bitcoin, like addresses from a private key and a public key, it's slightly different from how the how the hashing to find a certain like valid block, it's slightly different. So they're not completely the same, but in a sense, that could be very dangerous if, I guess, they didn't have these extra things on top of it that were trying to, I guess, like when you're dealing with like identity, if you didn't have those extra like factors or parameters, it might be very dangerous. So yeah. One last question before I move on. Yeah.
Yeah, so like, I'm trying to understand how this like actually verifies blocks. Because as I understand it, all we're doing here is just finding some random number, right? The knots that would add it to your previous block header and your Merkle root creates another random number with a certain number of leading zeros, right?
Yeah.
How is that verifying the legitimacy of the previous block, right? Because if I wanted to create a malicious block, I change some transaction which would change the Merkle root, but I can still find the random knots that would give me a hash with a certain number of leading zeros.
So the idea is that the question is, how does this actually verify like the transactions that go in the previous block? In a sense, it doesn't. In a sense, it doesn't. But the idea is that, on average, like it takes some computational work to, I guess, to include like these transactions into a valid block. If you were to try to include like malicious transactions or bad transactions into a block and you want to propagate that, if you're trying to do that by yourself, it'll take because you don't have, let's say all the power of the network at your disposal. For you, it will be difficult to do that because you don't have like the computational power to do so. You don't have all the resources necessary. If you're able to do that because you have a lot of resources, then that defeats the entire system.
So it really is just an arbitrary kind of problem just to add some sort of proof of work mechanism, but it doesn't actually verify the block.
Yeah.
It just discourages malicious activity.
It exactly, in a trustless environment, the way that you, I guess, try to discourage this malicious activity is that you make the malicious activity hard to do.
Okay.
Right. Okay. So the last thing I want to talk about is a Coinbase transaction. So Coinbase, not the startup, the actual definition in the Bitcoin blockchain is that in every block, we have to have at least one Coinbase transaction. Without this, the block isn't valid. The Coinbase transaction basically includes the mining reward and certain other aspects of it includes the mining reward and certain other aspects that make this block valid. Without any Coinbase transaction, you can't really do much. You can also have a valid block if you just have a Coinbase transaction. That's how the network started. But that's the main idea of what a Coinbase transaction is. It includes the mining reward and also other factors. And this is an example of what a block looks like. If we were to look back, or if you were to look in, let's say, the Bitcoin blockchain through a block explorer, you can find certain things that you can find certain, information about certain blocks. So let's say if we were to look at this particular block, we see that there's a certain number of transactions in it, 2055, and then we see that this is all the Bitcoin that it's dealing with and all the volume. And then the transaction fees is what you pay along with your transaction so that miners are more willingly or have an incentive to, I guess, take up your transaction into their verification pool. And that's just the amount of transaction fees that that are accumulated in that particular block. The height is basically the block number. So the height it's just a chain of blocks. The timestamp is when it was mined, and it's relayed by BTC top. BTC top is probably a mining pool that's been managed by a particular entity. And the difficulty at the time is, it's stated, it's that particular number, right? And if we take a look at the hash of this particular block, we find that there's a lot of zeros in the front of the hash. So this is the mining puzzle that we're trying to solve. We're trying to find some arbitrary inputs, the nonce, that make this output have a hash of a certain number of leading zeros. Does that make any sense? Does anybody have any final questions about like this section? Yeah.
Yeah, with the timestamp, like, how do you verify the timestamp? Like, if someone wanted to attack the network and they're mining it and they find a block and they put in like the wrong time, like, how does anyone check that?
The timestamp is more of like a arbitrary factor, because when you're actually mining, you can actually modify the timestamp to change up the puzzle. So I guess the timestamp is like there as like a general.
Right, but like if someone put the timestamp as like 2019, would that like completely mess up the difficulty setting?
I don't think that messes up with the difficulty. It's just the extra parameter that they include in a block. It's like just like metadata, but it doesn't really affect.
But that doesn't go into the difficulty adjustment?
It doesn't go into the difficulty. The timestamp isn't what's used. It's the how many blocks are mined in the past 2 weeks. That's the actual factor.
But how does it know what 2 weeks was?
I guess the protocol has like an internal timer that I guess adjusts every 2 weeks. It's not actually 2 weeks. It's like every 2016 blocks.
Okay.
Because if on average you have a block per minute that's released, it ends up being around 2 weeks. Does that make?
Yeah, I guess I
The timestamp factor or the timestamp parameter is just like metadata for a block.
Yeah.
It doesn't really change the difficulty at all. It's just an information tag. Does that answer your question?
Like you can see how many blocks have been mined, but how do you know how long a block took to mine?
Yeah, that's a good question. I'm pretty sure there's some way to do that. I can't answer that off the top of my head right now, but I guess when they're I can't answer that question right now, so I'll get back to it. Does anybody have another question? Yeah. Oh. So each block has, I guess, like a storage amount. So you can only include a certain, like, I guess, amount of transactions, or number of transactions. Yeah, so that's like a design choice by the. No, so the difficulty isn't by, let's say, the number of transactions that are included in a block. It's adjusted by the number of blocks that were mined in a 2 week period. So if that increases or if that decreases, it shows that there's an increase in computing power or a decrease in computing power, and adjusts based on that. It doesn't adjust based off of how many transactions are included in a block. So that's not like a factor that changes the difficulty. But the number of transactions that are included in a block is specified by, like, let's say, like the block size limit. So this block can only hold, like, let's say, this amount of data. And once I get to this number of transactions, my block is filling up with information, and I can't include anything else.
Would it affect malicious users? So if there's fewer transactions, then it's easier for another person to have that same branch.
So trying to mine a block has the difficulty tied to it isn't by how many transactions are included in it. So a block with just one transaction in it and like 50 transactions in it, they'll have like a similar amount of difficulty because what you're trying to do in the proof of work or the mining aspect is you're playing around with this nonce number to find a hash that will end up generating a hash of a certain number of leading zeros. When you have if you have one transaction versus 50, you still have a Merkle root and a previous block hash. Those stay like pretty constant, as in like the size of that. So those don't really change much about the difficulty of this hash puzzle. Like the aspect you're trying to play around with is this nonce number that you keep guessing until you find a certain hash that satisfies your target. Does that make any sense?
Yeah, I'm just going back, it's just like that's just some algorithm that you've done to get
Yeah.
it announced. So is it the previous blocks hash that sort of maintains that you have to be going to the right chain to be able to come on to the right block, or to be able to append this current block on that chain?
To append to like the next block is you have you know what's the latest block in the chain right now, and then what you're doing is you're taking that previous block hash, you're taking your Merkle root, which is the summary of your transactions, and you're modifying this nonce so that you get a valid block ID that that satisfies your requirement. It doesn't really it doesn't rely on like number of transactions. It doesn't rely on anything much other than these three components that I was talking about. So the previous block hash is included, the Merkle root is included, and the nonce. So these three aspects are what you're trying to play around with and find a valid block header or block ID. Does that make any sense? Okay, so next section will be.
We're gonna do a quick, like, 3-minute break. If you need to go to the bathroom, go. Like, stand up, walk around. I know it's a lot for you. We're gonna start at 3:05.
I'm sorry. How are you doing? For this? For other things?
I clicked 50 slides. 60
But
slides.
those are.
I'll provide some. Off Piazza? Or like for the class?
Also, you can
On Piazza?
really long question. You answer each question.
Oh, really?
And then I was reading it and I think I'm going to answer the second part.
So when the mine's mining,
Takeaways takeaways we want you guys to get from this. But then there will be some like key terms that if you're interested, you can go and look up on your own. So I'm going to try and explain this in plain English. So just to return back to what we had talked about previously, remember Alice has this private key, she has a public key, and she has a message. So she's going to use ECDSA to generate private and public keys. And so if you think back to lecture 1 again, the motivation for needing signatures is because we need to authenticate identity so that you know a certain message that you receive could only have come from this one person because it was signed by some specific private key. So you see, Bob has Alice's public key because that's sort of public information if we think back to the analogy of an email address. And Alice uses her private key to sign this message. So she'll create the signature, and then she'll send the message and her signature to Bob. And Bob will use, Bob can very easily verify whether or not Alice was the actual person who signed, because in order to create that signature, she had to have had the private key. So, and then this is like a key point, right? Bob cannot easily guess Alice's private key, and we want to like maintain that going forward. So Bob knows that the private key plus the message is equal to the signature, and the public key plus the signature is equal to the message, and so this is how he's going to verify and just like make sure. So is everybody clear about like these two statements? Okay, this should be like sort of relatively review. Okay, so if I have this third person, Eve, and she has her own private key and her own public key, of course, and she signs the same message with her private key, she's going to create a different signature. And so if Bob tries to verify Eve's signature with Alice's public key, that's bad, right? It's not going to go through. That's not a valid transaction. That makes sense to everybody? Okay, cool. Okay, so just to come back, like summary of this, recipients given the message and the signature pair should be able to verify the message origin, non-repudiation, meaning you don't want to be able to like find the private key, and then message integrity, in that the message cannot have been modified. So we know for a fact that that message has not been changed. Eve could not have changed the message, even though she might have like intercepted it. Okay, and so in this manner, we can guarantee that the proof of authorization is undeniable, in that like only one person could have sent a transaction if that's like what we've received. Okay, so there are no questions about this, hopefully. Cool, okay. So before we dive into the technicalities, I'm just gonna give you this goal takeaways. I want you to take a few seconds and think about this. Think about whether or not you have answers to some of these questions. This is the main like takeaway slide for this lecture. So if you can answer sort of some of these to yourself, then that's like awesome. If not, then that's what you should take to discussion this week, like trying to understand these things. But don't worry, because we haven't covered everything. So. But yeah, so as we dive into the technicalities, just try and relate things back to this slide. Okay, everybody had a chance to take a look. You can take a picture. We'll post slides. All right, cool, moving on. All right, so this is our first black slide, right? This is scary. Elliptic curve cryptography. So that's ECDSA. Bitcoin uses ECDSA. More specifically, Bitcoin's elliptic curve uses this SECP256 K1. This is all like, for high-level understanding, you don't really need to know this, but if you're interested, that's what the Bitcoin elliptic curve is. So what exactly is an elliptic curve? So the elliptic curve, remember we just said, the elliptic curve digital signature algorithm is used to find private and public key pairs. The mathematical definition of elliptic curve cryptography is it defines a finite abelian group that you can pose the discrete logarithm problem on. Don't worry about that if that sounds like gibberish. In English, it defines a mathematical function. Look at that pretty function. And it has a curve like that. And it's something called a trapdoor function. So we'll talk a little bit more about what that means. But just know that this curve is like what we use, and it's called elliptic curve cryptography. So moving on. So we pick a point P, and we're going to sort of like draw a tangent and see where, with P and Q, where does it meet? That's our point R. And then we're going to reflect that across the x-axis, and that's going to be our point, like P times Q. This is just sort of like the basics of how one would use a function in order to generate private and public key pairs. Again, we're not going to go into very much detail just because we only have an hour, and this is not a math class. But yeah, so just know it's something called point multiplication. So just like a little bit more elaboration. if we call that P, and that's our dot, and then we call that P, and we draw that cotangent. That's Q, or negative 2P in this slide. And then we reflect that across, and then we just keep doing this. You see how we drew a line to P, and then we recognize that there's another sort of intersection, and we take that intersection, we reflect it across again. And this is sort of like just the pattern that we go through. And we're going to repeat that n times, where our private key is n. So this might be a little bit confusing. I'm just giving you like a basic rundown of like how exactly we can relate it and sort of fit it into the framework of private key, public keys. But again, so our private key is this number n, and the public key is this thing that we've generated by reflecting things across the curve a couple times. Okay, and so the discrete logarithm problem then is, the main takeaway from that is that it's computationally infeasible. So ECC is a trapdoor function. If you don't know what that means, don't worry about it. It's essentially just that it's very, very difficult to sort of get the private key. And that is the main takeaway, right? Because it might sound a little bit like crypto magic that somehow like I have this function and like if I do stuff to it, then I can't find my private key. And I don't know really how that works, but somebody told me that that's how that works. So I'm just kind of giving you like a brief rundown. If you're interested, you can go and read further. But this is the basics of how this works. Okay. Any quick questions? All right, cool. Okay, so if we talk about how we go from a public key to a Bitcoin address, this is important just to understand the steps that are involved. So if we think about the motivation behind wanting to hash things, you want to protect your public key from exposure. So for example, when some people have asked, like, what if quantum computers exist? What happens then? So we can use quantum computers to break the public key potentially, but they can't break the public key hash. And so because, as Brian was saying earlier, all information is just digital data and zeros and ones, and we want to be sure that we can't like change, we can't manipulate the data in between. We want to have like tamper evidence, and we want that to be like a sort of invariant that we have. So we want to be able to make sure that every public key has like its deterministic public key hash, and we want to make sure that it's as protected as possible. So we're going to hash it twice with the SHA-256 and this thing called the RIPE-MD. So the RIPE-MD, we talked about SHA-256 earlier. It's used a lot. You're going to hear that a lot. But then RIPE-MD is just, it makes the hash smaller, less memory expensive, and that's really all you need to know. And then if we talk about the second half, the base 58 check and code. So it uses, the Bitcoin addresses use this base 58 alphabet. So when you create your hash, it's going to be some combination of those letters, and we have 58 of them, which sort of like should give you an idea of how many different combinations we could have. But with those 58, we omit 4, right? We omit the confusing like 0 and O, and then we omit the 1 and L. Sorry, L and I. That's it. But yeah, so that's sort of like a brief overview. And then what base 58 check and code does is it prefixes your address with this sort of version byte, and it ends your address with this checksum. So it's really difficult for people to remember like a really long hash, right? Probably what you're going to do is like copy and paste it and save it somewhere on your computer. So that's a really bad idea, first of all. Don't do that. Write it down in some like hard copy place and put that in a book you're not going to forget. But the checksum is at the end, and it's sort of like a summary of all of like the whole hash. It's computed so that you can have it easily at the end, and you can just sort of like verify that you typed in your entire hash correctly. And so it's built off of like everything that comes before it. And so with that, it makes it easier to very easily verify whether or not your hash is correct. Because again, they're like going to be very long strings of numbers and letters, and it can be troublesome to make sure. So decoding software often will use this checksum to validate whether or not your address is a valid one. That's just sort of an interesting aside. Okay, so any questions about that so far? Cool, all right. Okay, so how do you guys feel? Do you want to take a breather? We've thrown a lot of information at you today. Good to keep going? Okay, yeah, good. Thumbs up if we're good. Do we understand? Yes, okay, cool. So we're going to talk about Bitcoin script now. So Bitcoin script, how many people know what Bitcoin script is? Nadir, I know you know. Okay. So Bitcoin script is like, it's the scripting language behind Bitcoin. So we all know that Bitcoin is some sort of software that I can download on my computer. I don't really know how it works yet, but Gillian said some random stuff about like coins and blocks, and Brian has been talking about transaction times. But Bitcoin script is sort of like how we make it all work. So just to go back to some reminders, so Bitcoin uses an UTXO model, which maps transactions. So transactions map inputs to outputs, and you can think of each transaction as just like the summary of inputs and outputs. And then we're gonna like zoom in and talk a little bit more about like the actual structure of a transaction. But two things that we want to like make very clear here: transactions contain the signature of the owner of the funds. So if I go to a coffee shop and I want to buy coffee, I need to make sure that the only person, like after publishing that transaction, the only person who is able to redeem that Bitcoin that I just sent should be the coffee shop owner. And that's sort of like an invariant that needs to be true when I make a transaction, right? Okay, so spending Bitcoin is essentially just redeeming previous transaction outputs. And so that means that if I'm the coffee shop owner, whoever is paying me, I need to make sure that like only I am able to pay that. And so how do we go about, so this part is going to be about answering how do we go about making sure that the person we intend to be able to spend the Bitcoin is actually the person who gets to spend the Bitcoin. Okay? Okay, so this might look scary, but so these are the contents of a transaction. At the very top, we have the metadata, and so that's just like extra information about like timestamp, how many inputs and outputs I have, etc. We'll look into that a little bit more, and then you get the inputs and the outputs, right? Okay, so if we zoom in, this is like the part of the transaction that's the metadata zoomed in. So up here we have the hash, which is essentially the ID of this transaction. We have the size, the number of inputs, and the number of outputs that will follow. And then we have something called lock time, which is useful for scripting purposes. Otherwise, it's not super useful. We might talk about it later in scalability, but don't worry about it. Size of transaction, just like, again, just like extra metadata, and then the version number. Okay? So these, again, are just like, that was all housekeeping data. Now that we've gotten that out of the way, now we're moving on to inputs, right? This is sort of like the important part. So inputs, you see that we have two previous transactions being referenced. If you look up at the top, remember how we talked about input of this whole transaction ID at the very top? And then the vin underscore sz is 2, just saying that we have two inputs, which we do. And so again, these are the two previous IDs of the transactions being referenced. And then this is the index of the input in the previous transaction. So again, if you don't anticipate ever thinking about how the transactions go through, you don't need to worry about this, but it is really good to sort of understand what it is exactly that you're working with. So yeah, any questions about inputs right here? Yeah?
What do the hashes refer to?
So they refer to the previous transaction. So recall the UTXO model where we have to reference previous transactions. So that's just like the hash of the ID of the previous transactions. The same way that at the top of this particular transaction that we're looking at, it has its own hash ID.
So each transaction will have like their own deposit box. So this is a deposit box.
Yeah, you can sort of think of it like that, right? So this is a transaction that I'm trying to publish, and in this transaction, I have to reference like money that I have previously. So this is money that I have previously, and I'm going to output it to somebody else. Make sense? Cool. Yeah.
And where is the signature in this transaction?
Yeah. So we're gonna get to that. Yeah. Yeah. Quick.
What's the point of n?
Of what? N?
And index of input in previous transactions.
This is just telling you where to find it, right? So in my previous transaction, like my previous transaction is going to have a very similar format to this, and I'm going to have like input 1, input 2. So you just want to know like which one in the previous transaction you're referencing. Does that make sense?
Literally a line of code that.
Yeah, it's literally an index just like to make sure, hey, I'm making sure I want that one. It's just like housekeeping data. Okay, cool. Okay, if there are no other questions, we're going to go on. So this is the script signature. So this is a little bit more important, right? This is the signature used to redeem the previous transaction output. Okay, we're going to talk a little bit more about what that exactly means, but just know that it's in the inputs. Okay, and then if we move on to the outputs, this is the output amount. That's also kind of important. And then the script pub key, which is, this is a script. So it's something called an output script, which we'll also talk about. But yeah, this is in the outputs, and we have a value, and we have something called a Bitcoin script. And that's basically what you need to know for now. Okay, so questions about the contents of a transaction. Anybody confused about why we're including certain things in the transaction? Cool, all right, still have everybody. So Bitcoin scripts, all right? So remember we had just talked about our output, our output has this sort of weird long thing that's an output address, and I called it something called a Bitcoin script. So we're gonna break that down. This particular output script, essentially what it means is this amount can be redeemed by the public key that hashes to the address X, plus a signature from the owner of that public key. Can anybody sort of give me a rundown of why that's something we want? Did I lose everybody? Nobody understands why we need a signature? Seriously?
Well, you have to know it's the right person.
Yeah, okay, cool. So I still have one guy. What's happening with the rest of you? Okay, so yeah, I need a signature that makes sure that I can spend something, right? And I need to make sure that whoever is going to spend it has access to spend it. So this is what this sort of script pub key is doing. Yeah, so this is where we get into what exactly a Bitcoin script is. So script, or Bitcoin scripting language, is this language that was built specifically for Bitcoin. So for people who might not understand what a CS language is, that's like Python, it's like Java, it's just another language that was built, but it was built specifically for Bitcoin in order to do Bitcoin-specific things. Okay. Yes, okay. So now we're going to walk through an example. So it should be clear by now that outputs are pretty important. Yeah, so to make the input script work with the output script, you simply concatenate them, which sounds really hacky, and it is. But that's just how things work in Bitcoin. So the formal term for this is that our input script is called a script sig, which if we go back to the original, this is a script sig, right? So that's what's coming in from our input script, and then our output script is called a script pub key. And so if we put these together, we have a working script that Bitcoin clients can run to verify that a redeeming transaction is valid. Does that make sense? So this is sort of the mechanism on how we verify whether or not a transaction is valid. And our output script specifies a public key, and our input script specifies a signature for that public key, which is why we can only spend if we have both parts of the equation. Okay, and then a locking script is, essentially it found in the previous transaction output, specifies requirements for redeeming transaction. A locking script is the script sig. Okay, still have everybody. Broad overview, sort of understand. Give me a thumbs up if you do, thumbs down if you're really tired. Why am I not getting any reactions? Okay, cool. All right, so let's keep going. So we're just going to sort of break down what exactly that long string at the top means. So code execution, we have the script pub key, and then we have this opt up. All of these are just opt codes that will do stuff, that will tell the software to do stuff, and we'll go over what exactly that is. So just pay attention to the bottom. As we feed in things, we're reading down from on the left here, we're reading down from the top, and we're sort of loading instructions into the bottom here. So signature just sort of loads the signature, right? That's pretty straightforward, hopefully. That's the input signature. It specifies the signature and the public key. And it's just simply data instructions, so all you do is push these values into the stack, and then you get that's public key. And then opt up